So. All right, so adjust it a little. Okay, so can you all see the slides now?
We can.
Yeah. Are the slides visible? Yes or no?
Yes, yes.
Okay.
It's not on presenter view anymore.
Okay, super. All right. So then let's get started here. So problem solving. Okay. So first of all, right, so just a recap. So what is correlation? So it's basically just a way of measuring the extent to which two variables are related, associated with each other, right? And so I'm illustrating that here with two hypothetical rows of values or measurements, right? So for different participants or 30 participants, and so that is here in blue is the time, so these participants then spend studying, and in order to see the time as a score that they got on an exam. And a correlation just measures the strength, so both the strengths and the direction of a linear relationship between these paired data points. So paired means they come from so the same observation units, or they're related for a different reason. For example, if these observation units are matched, right? So just a reminder. So that's always the case when we have observation units that are, although they're not identical, so they share some association with each other, like could for example siblings or whatever. Okay, so strengths and direction and linear relationships. So what does that mean, right? So we will talk about that in more detail. So, but before we will do that, so if you look at these two curves here that represent some measurements. So do you think they are related? Do you think they are correlated? And if you think they are, why do you think they're correlated? And is it like a positive or a negative relationship, and why?
I can't even tell if it's a positive or negative because it just keeps going up and down and it's all scattered. Like usually with positive correlations, it's more there's a slope, you know what I mean? Like there's at least some type of slope going on, even if the data is scattered negatively or positively. I cannot tell with this.
Yeah, so this is not a scatter plot, right? So usually when you look at your scatter plot, right, at your cloud of data points, so you have so one variable on the x-axis. So normally, these views that you are more familiar with is that you have so for example study time on the x-axis, and then the exam score on the y-axis, and then you have your right, so your scatter plot, so your cloud of data points. This here is a different representation, right? So you just have one dimension, you have all the participants, and then you have the individual. So basically it's a one-dimensional representation, right? And then you have the data points for each variable along so this dimension, and here you have a separate graph that shows the data point for the other variable. So basically what you can see here is a variation, right? So of the values. So, and then with that in mind, I'm asking again, so do you think these two variables are related? Are they correlated?
Yes.
Yes, okay. Why?
They seem to have similar trends, even though the orange line is mostly always higher. It also goes down at the same time as the blue line.
Yeah, so very good, right? So that is a really good point. So it actually doesn't matter that the orange line is higher. So it just means it has a higher mean, right? So there's some like the values are, but it's just a scaling thing, right? So the most important thing, and that is what you just mentioned, is if the orange, right? If the orange values go up, the blue values go up too. So that means if I phrase it differently, right? If a participant has a high value, relatively speaking, so if you look at this profile here, right? If a participant has a relatively high exam score, they also tend to have a relatively high study time. And conversely, if they have a relatively low exam score, yeah, so like here, they also have relatively low study time. Yeah, so you see that here. So lower values are correspond to lower values. So you also see here, right? So these are lower scores, also relatively low study time. So that is a lower score overall. So the study time is So that's a low. So that's a lower study time overall. The exam score still, yeah, relatively good, but it's not a perfect association. But there's definitely a positive relationship between the two variables, right? So that is just basically a primer to remind you what it actually means that two variables are related, right? So if I'm high on one variable, then I'm more likely to be high on the other one as well. Yeah. So if you're talking about individuals, right? So. Okay, and also just a reminder, so what does linear mean? So when we are talking about correlation, so in this class, so we're also always talking about linear relationship. So that means how well the relationship between these two variables is represented by a straight line, right? And that makes sense when we look at the more typical representation of so the association between the two variables in a scatter plot, where each variable is plotted on one axis, so one on the x-axis and the other on the y-axis. Okay. So we have several examples of potential relationships here, so that range from a perfect positive correlation, and that will look more familiar to you, right? So that is a way that you normally see so relationships between variables plotted. So that ranges from a perfect positive correlation, right, to a high positive correlation to low positive correlation. Here we have this absolutely random distribution of the data points, right? There's no correlation. And then we are going here to a perfect negative correlation, right? And so and perfect positive means that it's a maximum strength, like perfect positive and perfect negative. There's a maximum strength of association between the two variables, so that it means that the points lie exactly on the straight line. Right? It does not matter what the slope of this line is, right? So that is the slope of the line. So it just indicates the direction of the relationship, but not the strength, right? So the strength is indicated by how well they can be represented by this one straight line. Okay. So, and you also know from previous classes that correlation can have a value anywhere between a -1 and 1, yeah, but not beyond these two limits. And so we also know that the sign indicates the direction of the association. Yeah, so the extremes are either 1 or -1. And so, right, so -1 indicates a perfect negative correlation, +1 indicates a perfect positive correlation. Yeah, so in both cases, you can put, so basically from knowing what's the value on, basically from knowing what the rank is actually on one variable, you know exactly what the rank is on the other variable as well. Right? And if you put that in a regression model, so you can predict the value of your second variable from the value of the first variable. Okay. Yeah, and when we are talking about a positive correlation, so we mean that as the values of one variable increase, the values of the second variable also increase. And as the values of one variable decrease, the values of the second variable also decrease. Right, so think of our introductory example with the time spent on studying and the exam scores. Yeah, so higher study times tended to go along with more positive exam scores and the other way around. Right, it was not a perfect relationship, but there was a clear pattern. Okay, so and that going back to this idea, what does linear mean, right? So, and the famous straight line. So you can see here, so an example where you have a correlation of 0.5. So, and while there is a positive association between the two variables, so that means, right, so if you have, right, so that is one variable, this is the other one here. So if you have higher scores on one variable, let's take this data point here, right, it's relatively high. You also tend to have higher scores on the other variable, right? So that is also here. And so, right, you can take another data point, this one, right, the lowest one on the X dimension here. So if you have low values on the first variable, you also have tend to have low variables on the second variable. But so this relationship is not perfect, right? So as you could see from this first point that I singled out here, right? So it's almost maximum on the first variable, but for the second one, it's at best just above the mean. So whereas so the relationship for this data point or this data point here is much clearer, right? So this is the absolute maximum for the first variable, and still for the second variable, it's almost right. It's a second largest value here in this on this dimension. Okay, but so it's clearly an association, but it's not perfect, right? So whereas here, if the correlation is 1, that really means that all values lie on this straight line. And we can have a perfect, not a perfect, now we can have a perfect association between two variables. So we can have, right, it doesn't have to be perfect, but so there can be an association that can be a systematic. So, but it cannot be described by a straight line. So, and in this case, the linear correlation would be 0. Right, so or a correlation value would be 0 if we have, for example, a curvilinear relationship or an inverted U-shaped relationship. Yeah, so it can absolutely be modeled, and it would be wrong to say those variables are not related. They have an inverted U-shaped relationship, so there's a quadratic relationship between the two variables. But the correlation, so the way we define it here and what's measured in the traditional Pearson correlation coefficient, would result in a 0 value, right? Because, right, as you can see here, so, right, so even, so if that is our, right, that's the first variable here, second variable. So having a low value on the first variable can go along with either having low values on the second variable, but it can also go along with having, so basically having high values on the first variable can also go along with having low values on the second variable, right? So there is no prediction possible. Okay. All right, so these are more examples, and so all possible relationships, right, between two variables and with the corresponding correlation scores, right? So we have here, right, our straight line, so 1, 1, so that's a strong positive association here, right? You can see the, so the slope has absolutely nothing to do with the strength of the relationship, right? It just has to do something with the direction of the relationship. So it is really whether it's a straight line or not that indicates how strong the relationship is, right? Not the slope. Okay, so and then for these funny data patterns here, so we all basically the Pearson correlation coefficient would give you a value of 0 because there is no linear relationship between the two variables. Okay, so I have a question about this one here. So, right, I left that open, so there's no corresponding correlation coefficient. So I was curious, what is the correlation for these variables? Yeah, if a data pattern like that. Basically a horizontal line. Yeah, so.
Is it 1?
Huh?
Is it 1?
Okay, 1. So that is one. Other suggestions? Okay, 1 is one suggestion. So are there other suggestions? I'm just curious.
But I don't know, because there's one in the other ones, but that one seems like a null or something like that because it's horizontal.
Okay, so yeah.
I don't know.
So you basically say it's null, so there is no relationship between the two variables. Are there any other suggestions? It's, of course, it's a trick question. So I'm always when I ask those questions, they're a trick question. So it's neither 1 nor 0. Any other suggestions?
If it's 0.5, you said it's neither 1 nor 0. I'm just saying.
Okay, so it's also not 0.5. So
Okay.
it's actually undefined. So why?
Oh.
So it is impossible to calculate a correlation for this particular case, because let's look at that. What does it mean, right? So we have again, right? So this, it's not basically, it's not drawn here, but let's think, let's just imagine here's a, so here's an x-axis and a y-axis. So that means the so we have variation along the x dimension, along the first variable, right? So there, let's assume that would be like our study time, right? So here, and then the exam scores there. But so what would that imply? It would imply that so all students have the same exam score. So the exam score is a constant. So what is the variance of so a constant? What is the variance for exam? Let's say exam scores 100. So all students have exam score of 100. What is the variance?
0?
0, exactly. The variance is 0. So that means the second variable is no variable. It does not vary, right? So in that, and as you may remember from your previous classes, so the variances, or the standard deviations of the two variables are in the denominator of the correlation formula. So that means we have a 0 in the denominator. And that means that it's not defined, right? So we cannot actually calculate a correlation here. It's not possible. And it also makes sense, right? Because if one variable does not vary, we cannot calculate a covariation, right? So I cannot calculate a covariation with a constant. That is not possible. So that is undefined here, right? So correlation is not possible to determine in this case. All right. So, all righty. Yeah, and then there are, I mean, for correlation, so there are plenty of research questions. So that could be answered using correlation coefficients and, of course, tests for significance. So like, is there a relationship between gender and student investigative interest? So yeah, note that. So I can also calculate a correlation. I can determine a correlation for categorical variables, right? So they don't have to be continuous. So we will talk about that later. Yeah, so the relationship between student achievement in math and English. Is there a relationship between the average bold response in certain brain areas and the corresponding reaction times to a certain stimulus, etc., 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 right? So a relationship between single trial responses of neuron A and B to repeated presentations of a single stimulus. So, I mean, I'm sure, so I mean, correlation is something that's relatively intuitive and I think easy to grasp. So you can think of other examples, and I'm sure you have used correlation in your own, so for your own research or your own research questions. Okay, and in all of these examples, we are always asking how strong are these linear relationships and what is their direction? So are they positive or negative? Okay. So when we measure correlation, so then we need to see whether two variables have values that change in the same direction, opposite directions. Yeah, or whether they change unsystematically. So whether that's in both the same and opposite direction, right? So in this case, we would have a 0 correlation. And so correlation is based on covariance, yeah? So how basically the corresponding deviations of the variable pairs relate to each other. And whenever we calculate the covariance, so we look at two random variables. Now let's call them X and Y. And we determine how much each score for these two random variables deviates from its corresponding mean. Yeah, so we look basically for a given observation unit, we look, so how much do the scores on the X variable for this observation deviate from the mean of X, and how much does do the scores on the Y variable deviate from the mean of Y. And if they both, if the deviations are similar, right? So if the amount of the deviation is similar, then we have a large covariance. Yeah, but if, for example, across all our observation units, but if large deviations, so from X, go along with either so large positive deviations, right? So go along with either large negative ones or large positive ones or small ones. Yeah, so then basically there's no association between the two variables. Okay. Okay. So I would like to walk you in some detail through the covariance formula, because it's important to me that you really understand so what it means, right? So, and that you also have like a sort of a mathematical or arithmetic understanding of covariance, because that is really, really important to understand. So this measure, and also what it means to have, for example, outliers, right? And what that means to this particular statistic. Okay, so it all starts with the formula of variance, right? So variance of a variable that you're all familiar with, right? So in order to calculate the variance, we take each measurement point, so each observation, and we calculate how much it deviates from the mean, right, of this variable. So we take so the square, we sum across all observations in our sample, and then we divide by sample size -1, right? So to make our estimator here less biased. Talked about that. It's still not completely, so so by dividing by n -1 instead of n, so we're making it unbiased, but it's not very efficient, right? So we're making it a little bit less, we're making it more variable across multiple samples. Okay, so it is, and we can interpret the variance as the average amount of data points, so of the average amount that individual data points or individual observations deviate from their mean. Yeah, so it's the average deviation of data points from their mean. Okay, so and when we're talking about covariance, so then we mean nothing but the average amount that corresponding individual data points, yeah, data points that belong to the same observation unit. Yeah, so the difference is just that we are now focusing on two variables and just on one. So the average amount that corresponding individual data points that belong to the same unit, to the same subjects, deviate from their means. So that means X from the mean of X and Y from the mean of Y, and the same versus opposite direction. So that is what covariance means. And so the formula is actually pretty similar to the variance formula, right? So we are just and instead of calculating or taking the square of these deviations from individual values from the mean, we are just focusing on cross products here. So otherwise, right, it's almost identical. All right. So, and when you think about it, or when you, actually we'll talk about that in a second. So how these plots can be interpreted here. But so if you look at a graphical representation of the covariance, so right, so we have our two variables here. So that let that be maybe X, and that is Y here. And so then here we have the case that the covariance is 0. Yeah, and so we see this nice symmetric shape here in all directions. It's basically as if you would take a normal distribution and would make it circular, right? As if you would take, basically, if you have a normal distribution and then you would turn it 360 degrees. So then you're getting this shape here. And the point is that, right, so take a certain value on your x variable. Let's say the x variable is 2, right? And then you look at the probability distribution, so the conditional distribution, right, of the y values for this x value. And you see it follows a normal distribution, right? So it's basically, so they have a maximum probability for the mean of y here, that is 0, right? And then you have this nice symmetric normal distribution curve here that is centered on 0, right? So that means it's basically the probability of having so in a certain, so basically, if you would have to make a prediction what your y value is based on the x value, you would have to come up with a mean, right? So basically, you cannot make any other prediction. So now let's look at what happens if we have a very small value, right? So we have -2. And then again, you see, right? So just look at one line here, right? So that goes, I mean, it's hard to see, but it's basically, right? So if you think about, you go a straight line, you walk over this hill here, right? And then down on the other side. So it's a normal distribution centered on 0. It means for both, for large and small values of your x variable, you predict basically, so the most likely observation on y, so the most likely value is a mean. So you cannot make any prediction, right? And the same is true for if you basically would look at it from based on the y values here, right? So no matter what x value you pick, so you will always have the highest probability of 0 for the y value. So it means that there is no relationship, right? So you cannot predict from knowing what your x value is. You don't know what the y value will be. So you have to, your best guess is a mean, right? Because it's the most likely value for y. But that the same is true if you wouldn't know anything about x. So what would you say if you wouldn't know what x is? You would still say it's a mean, because it's just the most likely, that's the expected value, right? That's the most likely value for this variable. So, and that's why, and a 0 covariance looks like that. However, so let's take a look at this figure here, where we have a positive covariance. So then we do the same thing, right? So if our x value is 2, right? So if it's relatively large, let's take a look at the corresponding distributions, the probability distribution for our y values. And now you see, so here the maximum is actually around 2, right? So now the conditional distribution, so if my x is relatively large, then actually the probability that my y value will be large too is high, right? So that is more, I'm more likely, it's more probable to get large y values. Yeah, and if you look here at the other end, it's hard to see. So behind the hill, right? You can think of it, if it's hard to recognize, it looks a bit like a fin, right? Like a fish fin or something like that. Here's a shape. If you look at the small value of x, right, and we see that so the probability distribution, the conditional distribution for y, so peaks at negative values for y. So that means, yeah, so for a large x value, so my best guess is a small y value. So I can predict actually from knowing what x is, what's the likelihood, so what's the most likely value of y is. So there's an association, there's a positive covariance, right? So just to let you know that what this representation means. Okay. So, and so just to keep developing this idea, right? So intuitively, covariance between x and y indicates how the values of x and y move relative to each other on average, right? So on average, across all data points, across all our observation units, right? So each of the observation units has 2 observations, one for X and one for Y. And if large positive deviations from X from its mean tend to happen with large deviations of Y from its mean, or if large negative deviations from X, so of X from its mean, tend to happen with large negative deviations of Y from its mean, then this cross product here is large and positive, right? So if you have basically if you have so large negative minus large negative times large negative, that's a large positive number, right? And so large positive times large positive is also a large positive number. So this term here is maximal if basically the axis and the y's deviate from their means in the same direction and by similar amounts. So then we have maximum number here in the denominator, right? So then the covariance gets really big. And so if we basically have a negative association, right? So if large deviations of the axis from their mean go along with large, basically, or if large positive deviations of the axis from their mean go along with large negative deviations of the y's from their mean, right? So then we have a large cross product, but it's negative. Right, so because we have the reversed signs here for each term, but still the absolute value is positive, right? It just has a negative sign. So that means there's a large negative relationship. So that means small values on X go along with large values on Y and vice versa. Yeah, and then the last case, so when is this term here, when is this cross product on average, right? So if we sum it up across all observation units, when is it null? So when is it 0? Yeah, that is when, so if large positive deviations of X from its mean happen with small and large, positive and negative deviations of Y from the Y mean, right? If there's no systematic relationship, so then on average that sum here will be 0, because sometimes it's positive, sometimes it's negative, right? Sometimes it's a small positive value, sometimes it's a small negative value, sometimes a large positive value, sometimes a large negative values on average will be 0. Right? If the other variable, if the deviates, basically if everything is possible, right? So for a small X, I can observe either a small Y or a medium Y or a large Y. So then this is 0. Okay, yeah, and so the n-1 here is the same logic as for our standard error, that just adjusts for the underestimation of the covariance by estimating the means of X and Y from the sample. Yeah, so rather, so using the true population means, so the same underlying logic. All right, so, and so this is just basically to make that clear for yourself. So the only difference between the formula of the variance and the formula for the covariance is that we are basically replacing, so this one x y minus x x bar with y I minus y bar. Yeah, so that means that rather than variance, we have covariance. Yeah, so and basically this formula stands for the maximum covariance, right? So it cannot be, the variance could not be any larger if I would replace the yi minus y bar with this term here, right? So that would be the maximum, if the identity, right? So if the values here would be identical. So that is our maximum relationship. Of course, it doesn't matter, so our maximum covariance. All right. So So there's, however, something that's not so nice about the covariance formula, right? So that's why it's not as commonly used as correlation. So that is, so the thing is that covariance depends on the units of measurement. So to give you a very a straightforward, easy example. So let's assume, so we have two variables that are measured in miles. Yeah? So, so the covariance between these two variables might be 4.25. Yeah, it could be something like, so average number of miles per day that, so people are working in year 1 versus year 2, right? So that could be. However, if I convert these scores to kilometers, then the covariance, changing nothing else, same sample, same data. I'm just converting, so the value, so basically the units from miles to kilometers. Now my covariance is 11. Yeah, that's not good, right? So that makes the covariance pretty useless. So because we cannot actually, it's completely dependent on so the units. So from, right, so like 11 sounds like a much larger covariance than 4.25. So, but it's actually the same association. So the strength of the association is the same. So that's not good, right? So we have to do something about that. So what are we going to do? We standardize it. So we make sure that we have the same units for both variables, right? And so we are just basically simply sort of transforming our variables into z-scores. And then our units are a standard deviation, right? So, so we basically express each variable in standard deviation units. Okay, super, let's do that. So we are transforming x and y to standard scores before calculations covariance. And this standardized version of the covariance is known as a Pearson's correlation coefficient, right? So that's what the correlation is. So we're doing nothing but, right? So we're converting our scores to z-scores. Yeah, that's what's shown here. So we subtract the mean and divide by the standard deviation. And then we see that just corresponds to the covariance divided by standard deviation of our two variables. And that is the reason, right, if we think back to this introductory example, that exactly is the reason why the correlation for this horizontal straight line is not defined, right? Because sy was 0 here. That means it would make this entire denominator 0, and we cannot calculate a correlation. Fantastic. So now we have a measure that's absolutely not dependent on units. And so that means the correlation of 0.8 is the same for whatever unit I choose to measure my variables, right? So that's good. Okay, so it indicates the same strength of the association. Okay, so many good things. So we know, we have already mentioned that, so the correlation coefficient always varies between -1 and +1. So bivariate just means the relationship between two variables, right? So always bivariate means relationship between two variables. And so correlation also has another nice feature, it's an effect size. Yeah, so, and there's like a rule of thumb or some convention, right? So what R values correspond to, so what effect size classifications, but that's really absolutely arbitrary. So these are simply conventions, right? So what's a convention? So that was introduced by Cohen, suggests that, so we consider an absolute value of correlation coefficient of 0.1 is a small effect size, 0.3 a medium effect size, and 0.5 for a large effect size. Yeah, but that's, again, true. It's mere convention. So you may also know, and we will talk about that in length next week when we talk about regression. So that if we take the square of our correlation coefficient, then we get the coefficient of determination, and the R squared value is gives you the proportion of variance in one variable that is shared by the other, right? So it's the proportion of variance that two variables share. Yeah, and it's of course, so both variables are basically are standardized and have a standard deviation of 1 in this case, right? Otherwise it wouldn't make, so so that is what the correlation automatically does, right? So to each variable. So we just introduced Pearson correlation as a measure of the strength and the direction of a relationship between two variables. So it means when it's 0, there's no correlation, so there's no association. But when it approaches -1 or +1, there's a strong negative or positive correlation, association between the two variables. But is that all that we need to know? Is it enough? So is it basically, if I was interested, if I wanted to test the hypothesis that so there's a non-zero correlation between study time and exam score. So then I collect data. So I have my sample. I calculate the correlation coefficient. I determine the correlation coefficient is 0.34 for my sample. So is that all I need to do? But am I done? And I say, fine. I've determined that so the correlation between study time and exam score is not 0. So is that enough? Yes, no. What else do we?
I was gonna say no.
That is correct. So what do we need to do? Let's maybe we start one step earlier. So why is it not enough?
It's not enough because it doesn't if it shows no correlation, then it's not strong enough. Therefore, you need to find a different variable that like increases its strength or something like that. I don't know.
So okay, I'm not quite sure, but so but I fully understand what you just said. So basically, so again, so let's go back to this example, right? So I have my sample, and I correlated I calculated the correlation coefficient, and I found the correlation coefficient for this sample was 0.34, right? And so what I wanted to know is whether the true correlation, the population is significantly different from 0.
Okay.
So what do I need to do? So why do I need to do more? Why can't I conclude from my sample correlation coefficient that so it's also true for the population as a whole?
Do you need to know?
So yeah, Allison, go ahead. Sorry, Camille.
Do you need to know the standard error?
Yeah, so right. So okay, so it's absolutely. So we need basically. So the reason is that it might be just a sampling error, right? So we just have a small sample from a big population, right? So I mean, if all we were interested in, if that was one class, right, and all I was interested in was to know what is an association in this class, and I'm done. Yeah. So if I wanted to know that, for example, for our course. So then I would ask all of you, how long did you study? So then I would say, what are your exam scores? Fine, I'm done. Right? So because that's all I'm interested in. However, if I want to generalize to a larger population, then my correlation coefficient of 0.34 that I obtained for my sample could actually come from a population that has a true association of 0 between the two variables. It could just be sampling error, right? So just right, even I mean we know that, right? So if we draw samples from a population, so then by mere chance, we can. And by sample error, I don't mean that so that you drawing a random sample. It just means that because you're picking a subset of the population, just by chance, it might happen to be the case that you get a correlation coefficient of 0.34 for this sample. Right. So if it's what is the expect basically the sample. So Alison just correctly mentions the sampling distribution, right? So if we sample from a population that has a true correlation of 0 between study time and exam anxiety, then on average, yeah, our sample correlation coefficient will be 0. But we might have samples where, right, depends on sample size. But so we might have samples for how is it? Distribution is shaped, the sampling distribution, right? But so we may have samples where the coefficient is 0.8. Unlikely, but it's possible. And the smaller the sample, the more likely it is. So we might have samples where the correlation coefficient, the sample correlation coefficient is 0.34. So we might have samples where it's negative, right? So that is just due to the fact that so there's a randomness to right? So we are not studying the entire population. So we need to run a significance test. We have to determine how likely is it, right? So if how probable is it that if that sample comes from a population with a true correlation coefficient of 0, how likely is it to get a correlation coefficient of 0.34 for a sample that size? That's what we need to do. So we have to make an inference, right? So we're making an inference from our sample to a population of interest. Okay, so and Alison absolutely correctly noted we need to know the sampling distribution. So and we know that the so if we are testing the hypothesis that so this correlation coefficient comes from a population with a true correlation 0, then we already know that the mean of the sampling distribution is 0. And you can also determine the standard error of this standard deviation of this sampling distribution, so the standard error of this statistic, right? Okay, yeah, so Pearson's R, it's nothing, but so if we calculate that for our sample, Pearson is just an ordinary statistic. It's like a mean, it's like a sample mean. Just happens to be, right, an R, so a correlation. But so the logic is exactly the same, right, for this idea of testing and sampling distribution, right? So we're calculating statistic from our sample, and then we have to look at the sampling distribution for this statistic to determine how likely it is to obtain this statistic if our null hypothesis, right, is true, given the assumptions about the true parameters, in this case about the true correlation in our population. All right, so let's make that more concrete by talking about an example. So assume that so the correlation between quantitative and verbal SAT scores in a given population is 0.6. Yeah, so that is our true population parameter. And in order to differentiate that from the sample parameters, so from the sample correlation, so it's right, we use a Greek letter. So and it's rho. Yeah, so our population parameter rho is 0.6. So let's further assume we randomly sample 12 students from that population. And we calculate what the sample correlation R is for these two students. And so then we would, so it will never be exactly equal to 0.6, right? We might get all sorts of values for our sample correlation. Okay. So and if we draw different samples of 12 students, so each time we would get a different value for R. Yeah, and if we do that in an infinite number of times, yeah, so if we draw 12 students over and over again for each sample, we calculate the sampling distribution, the sample correlation. So then we will end up with our sampling distribution for this sample statistic R. Okay. Alrighty, so and here, right, so in this nice graph here, you can see what this sampling distribution for our example looks like. So for a population, right, so with a true correlation coefficient of 0.6, if we draw a sample of size R, then the sampling distribution of R looks like that. You can see it has a negative skew. So, and the reason for this negative skew, which was not supposed to show up here because I wanted to ask you, but unfortunately it's already there. So the reason is that R has limits, right? So R is limited. R cannot be larger than 1. Yeah, so that means that the distribution cannot extend as far in the positive direction as it can in the negative direction, right? So remember, so the true parameter is 0.6, right? So in our population. So that means that we can deviate much more. We have until -1 in this direction than we can in this direction. So there's like some natural cutoff here. And that is the reason why the population distribution is skewed. Right? So if our population parameter would be negative, we would see the opposite pattern, right? So if we had like minus 0.6, so then our population distribution would look like that, right? So we would have a positive skew. All right. Yeah, and so in general, so the greater the value of our rho, so the greater the absolute value of our population correlation, so the closer we get to 1, the more extreme is the skew, right? Because of course the problem is getting worse. So we're having less and less options to vary, right, in this direction.
Yeah, why has no one? Why is no one on the teach?
Okay, so and so if we want to make a statistical inference, right? If we want to make an inference from our sample to the underlying population, so what we are basically doing is we're just looking at the sampling distribution, right? And we compare that with our obtained sample statistic, and we check, so how likely, what's the probability for this sample statistic under the null hypothesis that this sample comes from a population with this true parameter. So, right, so this is our true parameter. So that means if we would, for example, get a sample statistic of minus 0.3, like here, so that would be highly unlikely, right? So very unlikely that if the true population parameter is 0.6, that we would get such a low number. However, if we get 0.8, so that is much more likely overall, right? So, okay. All right, sorry, 1 second. Close the door here. My daughter just locked the door in my hospital. It was locked out. Okay. All right. So, okay, so far so good, right? So the logic is always the same when we're running a significance test, right? The problem is, so if you go back to this distribution, right? So because it's skewed and looks sort of funny, we actually can tell, so from without making any other assumptions, we actually can tell for sure how probable that is. So we right, so if it would be a normal distribution, we can tell exactly what the probabilities are because we know that for the normal distribution, right? So we have R, we have the table, so that is a known, right? So that is the beauty. That's why the normal distribution is so important in statistics. So we would be able to tell exactly what the probabilities are that, so the scores are here or here or here or here or here or here, right, for our sample. However, since it's a funny skewed distribution, we don't know, right? So we don't know, usually don't have a sampling distribution. So if we don't know it's normal, then we are sort of screwed. So that is problematic. So we cannot run a significance test. So what can we do in this situation? And so thankfully, I mean, there are many things that we can do. But one workaround has been developed by Roland Fischer, so famous statistician. And basically he developed a way to transform our sample statistic R into a variable that is called ZR, and that variable is approximately normally distributed under certain assumptions. So certain assumptions have to be met. So, and we also, so not only so that he came up with this transformation, he also came up with a way to calculate the standard error for this transformed variable. So cool. So that means we know everything that we need to know. we can just so we can transform our R into a new statistic that we know is approximately normally distributed. We know the standard error for this new variable. So that's cool. So that means we can run our statistic, so our hypothesis test. We can now determine exactly how probable it is to get a given value for the statistic under the assumption that the null hypothesis is true. Yeah, and so this is the standard error, and that is here how we calculate our transformed z value. So it's the logarithmus of 1 plus r over 1 minus r and times 0.5. Okay, let's so illustrate that in an example. So let's assume the question would be that we want to know what is the probability of getting a sample correlation of 0.75, right? So if we calculate that per a sample in or higher in a sample that has 12 subjects, so 12 observation units, from a population that has a true correlation of rho 0.6. So how likely is it that I will get 0.75 or higher if my true population correlation is 0.6? All right, so first thing that we have to do is we have to convert both, right, our population correlation and our sample correlation to their corresponding z values, right? So we have to use this z, so R to z transformation that has been introduced by Fisher. And we have to calculate the standard error for these transformed variables. Okay, so let's do that. So for our population correlation, the value would be 0.693. And for our sample correlations, the value would be 0.973. So we can just plug that into the formula. And then we calculate our standard error according to the formula on the slide above, and that would be 0.333. 0.333. All right, so, and we know that, so these, basically, so that the transformed scores are normally distributed, yeah? So as a given a normal distribution with a mean of 0.693 and a standard deviation of 0.333, so what is the probability of obtaining a value of 0.73 or higher? So that is a new question that we are asking now, right, after this transformation. So we have the new, right, this is our new true population parameter, right, so our transformed population parameter. This is our new transform test statistic. That is the standard deviation for the sampling distribution for a correlation from a population with this parameter. And now we want to know how likely is it. Yeah, so and what do we need to do? Yeah, we have to find the corresponding z-score. How do we do that in R? Everybody should know. So if I would ask you, what is a z-score? So for, no, I'm a little bit ahead of myself. So first we have to transfer basically one step at a time. So if you would put that into R, right? So if I would ask you, what is a probability? So if we are talking about a normal distribution. So what is a probability of getting for this a variable here, of getting a value of 0.973 or higher for a normal distribution that has a mean of 0.693 and a standard deviation of 0.333. So what would you do? You sort of have to do it in your assignments, so that's what everybody should know.
Is it P norm?
So yeah, so that would be the second step, but what do we have to do first? Because P norm, I mean, yeah, you can use P norm, you can, but then you have to specify, so the additional, can you do that? With P norm, I don't actually, I'm not 100% sure whether it gives you the option to set the parameters. Can it? I have to look that up. I never do. So let's assume okay. Let's assume the following. Let's assume your R can only tell you the, so your P norm, you have P norm function that can only tell you the probability for a standard normal distribution. So a normal distribution with the mean 0 and the standard deviation 1. So what would you do? But you know that you have a distribution with a mean of 0.693 and a standard deviation of 0.333. So what do we need to do first? Naja, I mean, it's already there. Maybe that's why you don't say it. So we have to transform it into z-scores first, right? So by our usual transformation, right? So using the usual formula. So we're taking our correlation value, we are subtracting the mean, so the true mean, and we are dividing it by the standard deviation, right? So that means we're taking our correlation coefficient, we are subtracting the true mean, and we are dividing by the standard deviation. So we come up with 0.84.
Mama, but where is the book that Oma has a sheet here?
That's in your cabinet, my dear, and where the other stuff is, the crown, etc. Okay, so and so if we then use our nice P norm in R, right? So we can get the probability of getting a z-value of 0.84. Yeah. So and that probability is about 20%. So you can check that. So on R, right? So of course, either use the upper tail option or the lower tail argument in your P norm function, or you just calculate the 1 minus P norm of 0.841, and then you get the probability of obtaining so this value or higher value. All right. Yeah, so and then we can conclude, so that's a probability of getting a sample correlation of 0.75 or higher from a population with a true correlation of 0.6 is about 20%. Oh, it's pretty likely, right? So that would not force us to, or that would not make us, would not convince us too much that it's necessary to reject the null hypothesis, right? We say, okay, we're relatively comfortable with keeping that null hypothesis. So, in most cases, right? So if you're doing your research yeah, so it's very, very common that you're actually not testing the assumption that your sample comes from a population with a true correlation coefficient of 0.6 or whatever. So in most cases, you want to know whether there's an association or not. So you're basically testing whether so the correlation coefficient, so the true correlation coefficient is 0. So that is in most cases true. And so the good thing is that if you're testing this hypothesis, right, if you're testing against a null hypothesis of a 0 correlation, then the distribution of R is symmetric. Yoo-hoo, so that's great, right? And the reason is that it can deviate in both directions the same amount, right? So if we have a 0 population correlation, so then we have this nice symmetric sampling distribution for R. So that is super, because it makes so the statistical testing much easier. And if that's the case, right, if you're testing your null hypothesis of a 0 relationship, so zero correlation between two variables, and your test statistic is actually t-distributed, So you can find a test statistic that follows a z distribution, a t distribution, sorry. And so the reason that it does not follow a z distribution is that, again, so that we work with means that we estimate from our sample rather than the true population means, right, when we calculate the correlation. Okay. So this is just a side note here. Actually what happens with the sampling distribution as our true population parameter approaches +1 or -1. So what happens if we sample from a population that has a true correlation of 1, so or -1. So in that case, so the sampling distribution actually is not really a distribution. So I mean, is of sorts, but it has a standard deviation of 0. Because if we basically sample from a population with a true association of 1, if you have a perfect relationship, then for all samples that we draw from this population, necessarily the obtained correlation coefficient must be 1, 2. Yeah, so there is no other option. If we have a perfect association in the population, then our samples all must have a perfect correlation as well. So then we have there's no variability in our samples. So that's just a side note. Okay, so and so as I mentioned before, if so our null hypothesis assumes that there's a 0 correlation or close enough, right? So as long as it's probably smaller than 0.3, so then the standard error for our correlation coefficient can be estimated according to this formula here. And I mentioned before, so this so the test statistics follows a t distribution. So that can be calculated as follows, right? So we just, as usual, so we subtract the true population parameter, in this case 0, from our observed correlation, and then we divide by the standard error, right? And then we end up with this formula here. And our degrees of freedom are n-2, and the sample size -2, and again, so we are losing 2 degrees of freedom because we are estimating our means, right? So in order to calculate the correlation, so you see that in this formula we have the correlation coefficient, right? And to calculate the correlation, we need the sample means, right? So and we don't have, so we need the sample means as estimates of our population means. So so for the same reasons that the standard deviation is that this introduces an additional degree of uncertainty for estimating the standard deviation. So it introduces an additional degree of uncertainty for estimating our correlation coefficient, right? So in here we're estimating 2 means, not only 1 for the standard deviation, but 2, right? So 1 for each sample. So that's why we're losing 2 degrees of freedom. Because now, so again, with the degrees of freedom, so the logic is that after you basically, right, so if you know that so for your variable x, so you have to have mean, so the mean that you calculated for your sample, then only n minus, so if n is the sample size, and only n-1 values are free to vary, right? Because the last one is determined by the mean, and the same is true for your other variable y. Yeah? So that's how you lose the 2 degrees of freedom. Okay, so yeah, so let's again talk about that using example. So let's assume we observe that's a correlation between literacy rate and political stability in 10 nations. Is 0.5. Yeah, so in this case that's actually also a nice example. So what are the nations in this case? Sorry. So what are the nations in this example? I mean, I don't ask you what the concrete nations are. I'm asking you what is the I just want to make sure that the example is clear. So, well, let me phrase the question the other way around. What are the observation units in this example? What are the subjects?
That the nations are the population and the literacy rate and ability are.
I don't find it where my other where my cousin and I don't find them anywhere
Okay.
where that is. That's where I don't find
Exactly, right? So we have, so in this case, we're completely right. So in this case, our nations are the observation units. So these are basically our subjects. And so for each nation, we have two observed values, right? So or X and Y, so our two variables are literacy rate and political stability. So for each nation, we have one value on literacy rate and one value on political stability. Right, so I have a sample size of 10 here. So I'm always trying to make these cross references to make clear that we're not talking about animals or humans or participants, so that observation units can be everything, right? So that's just why I was pointing that out. Okay, so and now we want to find out what is the probability of obtaining, so from maybe take a random sample, right, of obtaining a correlation coefficient that is that large, right? So a sample correlation of 0.5 or higher, if so the 10 nations actually come from a population with a true association of 0, so where literacy rate and political stability are unrelated. Okay. So, and let's first assume that our willingness to reject our null hypothesis is 100% if the probability is less than 5%, so that we're basically willing to reject the null hypothesis if the probability to obtain that sample coefficient is less than 5%. Okay, so first we calculate our test statistic, right? So according to the formulas that we just talked about, so our T statistic here is just the sample correlation coefficient multiplied by this expression here. So, and right, so it's the n sample size minus 2, so divided by 1 minus so 0.5 squared, and this is just 1.63. So this is our T statistic. Right, so and of course we have to multiply it by so R, which is in this case is 0.5. So, and then we use a table or the or R to determine the quantiles of the T distribution to find the probability of getting the T value that is 1.63 or above. So what function are we using in R, and what do we have to tell this function? What arguments do we need? What R function are we using? I mean, you don't really have to do that in R because it will calculate a t-test for you with using a separate function. But if Dr. Unger would ask you to do that in R, so how would you do it? How are you getting the probability of getting a t-value of 1.63 or above?
Is it PT?
Mm-hmm. And what do you have to make it? So what do you have to give it? So what parameters do you need? I mean, obviously the t-value itself, but what else? So what else? Does PT want? Otherwise, it cannot calculate it for you.
Whether it's positive or negative?
It's something that P norm does not want, but PT does want it. Because the T distribution varies as a function of What does the shape of the t-distribution depend on? Is it always the same? No. We have multiple t-distributions, right? So probability distribution looks a little bit different. And what does it depend on?
Standard deviation.
Not just that, yeah, that's one parameter. Yeah, so no, what determines what the standard deviation for example, for a t-distribution is?
Would you mind repeating the question?
Yeah, so what basically we have, so the t-distribution looks different, right? So we have multiple t-distributions, or probability distributions. So what does the shape of the t-distribution depend on? Right, we have one standard normal distribution, but the t-distribution is a family of distributions. So it varies. And what does it depend on? What it looks like.
I think Anjali said, took a guess and said degrees of freedom.
Ah, okay. Right. I probably did not hear that. So yeah, absolutely, the degrees of freedom, and that is nothing but the sample size. So what is the degrees of freedom here? What do we have to tell R?
Degrees of freedom are 8.
Yes, very good, 8. Awesome. All right. So yeah, and that's how we would do it in R. So you can also use the lower tail option argument if you want to do that. Okay, so that means the probability of getting a correlation coefficient that high or even high, so basically that high or lower than 0.5 is actually so around 7%. So that high or higher was right in the first place. So basically, so the probability of getting a correlation coefficient, so that extreme, right? So is 7%. And so that is just above our predefined threshold of 5%, right? So that means we would keep the null hypothesis in this case. So it is not super likely, but it is within our range that we feel comfortable accepting or keeping the null hypothesis. All right. So how do we calculate confidence intervals for Pearson's R? Right, so our Pearson's R is nothing but a point estimate. Yeah, so R, or sample R, is a point estimate of the true underlying population parameter rho. So, and now, so we want an interval estimate. So we want a confidence interval. So how do we calculate that? So problem is that if our population parameter is unequal, so does not equal 0. So we have, so our confidence intervals around Pearson's are not symmetrical. So that sucks. So what are we going to do, right? So we use Fisher's R to Z transformation. So that will help us with the confidence intervals as well. So we're doing the same thing that we did when we performed the significance test. So we're just transforming our R value into Z values. And then we use these Z values to calculate our confidence interval in absolutely the same way we would do for, right? So for the for any other statistic. Yeah. And then of course, so this confidence interval here, if we calculate that, so using so these transformed values, right? So we would basically transform our point estimates, so our correlation or sample correlation coefficient into a Z value. by using this formula. And then, so we would use the, so our standard normal distribution, the quantile, for to estimate our basically how wide our confidence interval is. So so our margin of error here. So then everything would be in these transformed z values. And this is a little bit odd, right? Because we don't know how to interpret them. So what do they mean? So these d values, they're not really a correlation, right? So they're transformed correlations. Well, that's not good, right? So and what we need to do is we have to convert them. So we have to convert the upper and lower limits, so the boundaries of our confidence interval, back to normal R values, right? So back to normal correlation values, and we can do that using this formula. So we're just reversing what we did. So basically just reversing the transformation. All right. Yeah, so, but a general piece of advice. So when it comes to estimating the confidence interval for Pearson's R, I would always use bootstrapping to do it. And I think it's also the standard in R. If you ask for calculating confidence intervals, we will hopefully be able to do that next week, next Monday. And so the idea here is, so the same ideas that we introduced when we were talking about bootstrapping the first time. So we have our sample, right? We have n pairs of observations. So we have n subject observation units in our sample. And if you're repeatedly resampling, so from our observed set of n pairs, and we calculate the correlation coefficient for each sample. So important that we sample with replacement, right? So we can put them back. That's how we get variation in our samples. So then we do that many times. So then we can approximate the sampling distribution of R, right? So we can basically simulate it, and that is leads to much better estimates than so using the R to Z transformation. Especially under certain circumstances. Okay, so again, so when we talk about or when we calculate the correlation and want to so basically going to calculate confidence intervals and want to run significance tests, then we have to make sure that certain assumptions are met. And so the first assumption is that, of course, our variables are measured at interval ratio level, so the scale of measurement. So we have to make sure they're linearly related. That is not necessary. It does not, otherwise it does not affect the statistics or the conclusions. It just means that we can only catch, right? So a linear relationship is a correlation coefficient. So, right, so it's not that we are biasing the statistics or so. And so that is very important. So the two variables have to be have to follow a bivariate normal distribution. So that means they have to be individually normally distributed. And so for each value of one variable, the corresponding value of the other variable has to be normally distributed, right? And that is again here illustrated in this figure, right? So for each value of X, so the distribution of the corresponding Y values has to be a normal distribution. So that is what's required. So that by this assumption of bivariate normality. And again, so normality only matters if you plan to compute significance test or if you use non-bootstrapped confidence intervals. So if the normality assumption is violated, so then you can still bootstrap. Yeah, and you can still also, you can do bootstrap to estimate to determine your confidence intervals. And you can also do bootstrap or like a closely related method, it's called permutation testing, to determine the significance or to test hypothesis about your correlation coefficient, right? But you cannot use the Fisher's R to Z transformation or so to get your normally distributed test statistic or so the T distribution, you cannot use those measures. If you have strong deviations from the normal distribution. Okay, so and so we were talking about estimators and bias at the beginning of this class, and so just so you know, Pearson's R, so the sample correlation coefficient, is an biased estimator of the correlation, of the true population correlation. Yeah, that's for similar reasons as the standard deviation is not an unbiased estimator of the population standard deviation. So, and it can be shown that for that the expected value of the correlation coefficient in samples from a normal population is slightly less than the population correlation, so that underestimates. So we have slight underestimation of the true population parameter. So the bigger problem is that so this might affect the type 1 error rate. Yeah, so the basically the probability that we reject the null hypothesis despite the fact that it's true. So for the t-statistic, so the type 1 error rates and the probabilities remain fairly close to the true significance levels, even if the so the variables are not bivariate normally distributed. Yeah, so the t statistic is more robust. Not for all non-normal distributions, but if we don't have like an extreme skew or so other like so substantial deviations from the normal distribution, we are good. So the R to Z transformation, however, can lead to really large distortions if our variables are not normally distributed. So if they're not bivariate normally distributed. So if we have deviations of the normality assumption and we use the R to Z transformation and then the standard normal distribution, so test for significance, so then we we run into so a problem that our conclusions might be invalid. Yeah, so then we might have amplified or type error rate might be much higher. So that is an issue, and that's why normality. So testing the normality assumption is very important. And if you're not sure, it's better. So at least you should use the t-statistic and not do the R to Z transformation, or you should use bootstrapping or permutation testing. All right. So there are other issues in so when determining correlation coefficients that can threaten the validity of our conclusions. So, and the most important one are outliers. So both univariate or bivariate outliers, right? So univariate outliers are just outliers on one of the two variables, so that are just extreme values that are like, for example, certain number of standard deviations away from the mean, or just be distant from the majority of the other observations. And bivariate outliers are so basically certain great distance from the envelope that basically describes the scatter plot, right? The central envelope of the scatter plot for the two variables. If we plot one variable on the x-axis and the other variable on the y-axis. It is also influenced by the magnitude of the slope around which the points are clustered. It is influenced by the magnitude of the residuals, right? So how much the individual data points deviate from the straight line that so that can be that is used to estimate the relationship or describes the relationship, and it is influenced by the restriction of range. So and one so this last problem is actually pretty common. And that's why I wanted to say a few more. I mean, we will talk about the other issues as well, especially outliers. But so the last point is, so the problem is that if we estimate the correlation between two variables, but we basically select on one variable only extremely, so we our sample has an extremely small range on one variable. So let's assume, take, I don't know, Princeton University. Right, so and they're super competitive, right, in admitting students. So you only get, well, most likely you get into Princeton only if your GPI is pretty high, and the GPI is very narrow. So basically, the students that get admitted to Princeton, so basically they represent a very limited range of GPAs compared to the whole distribution of possible GPAs in the student population. Right, so here you have an extreme limited range in one variable. Let's now assume that Princeton would calculate the correlation between GPA and their grades in college. So then there was other performance measures. So then, sorry, I'm not familiar with the American system. I meant for, of course, the SAT scores of students who apply to Princeton. And then, so if you would correlate these SAT scores with the GPA scores, that's basically the grades that they have in college, so you will probably find a zero correlation. Yeah. So despite the fact that in the population, if you basically take the entire population, if you do not focus on Princeton only, but if you take the SAT scores from all students in the United States and then correlate with their college GPAs, so you find a positive correlation. But right, for this Princeton samples, the correlation would be zero because the variance is so restricted. And think about what is a correlation, right? A correlation coefficient tells me how much variance can one variable explain in the other variable. So how much variance in the GPA can be explained by the SAT scores. Yeah, if my SAT scores don't vary, they can also not explain any variance in my GPA, right? So that is the reason, so just intuitively. So we have to make sure that we're not artificially restricting our range, right? So that has also an effect on the correlation coefficient. All right. Yeah, and so Pearson correlation is really, really sensitive to these issues. And so that can basically lead to both, can lead to false positives and false negatives. So we're of course more concerned about false positives. It's also more common, but false negatives can be an issue too, right? So if I overlook, if I come to the conclusion there's no correlation where there actually is one. So in some cases that these issues can mask a true correlation. In most cases, they will make the researchers believe there is one where there's none. All right. So and here that is so it is just a graphical illustration of the problems that I just mentioned, right? So if you have a restriction of range, right? So if that is the right, if we basically so these are the SAT scores, right? So this is our GPA. This is the entire population of students. And then we would basically take, all right, so if we have our Princeton sample, that's an exaggeration, is of course not that large, but if we basically choose the sample so that the range is restricted on X, so then the corresponding correlation will be underestimated, right? Okay, so and we can also do the opposite, right? So we can draw a sample that actually overrepresents, so it exaggerates the range, so the variance on one variable, right? By basically sampling from these two ends of the distribution, right? So if I only pick students with very low SAT scores and students with very high SAT scores, and then I estimate the correlation between SAT and GPA, and actually overestimate the true correlation. These are just illustrations of all sorts of sampling errors that result in misrepresentations of the true correlation, so basically in misrepresentations of the true correlation, so that are based on estimates that we make from our sample. Okay, so because I just want to talk at least a little bit about outliers, that's why I'm moving forward here. And so I mentioned that before, right? Outliers are a pressing concern, especially if our sample is small, because then they are more influential in most cases. So here you have an example for a fictional data set with one outlier. And so the correlation actually without the outlier is 0.5 between these two variables. So the correlation including the outlier jumps to 0.48. Yeah, so we can see how much so this single value here contributes to our conclusions about what the what's a true association between the two variables might be. And the problem is that we don't know, right? So we basically, there's a gap here between the X values, right, of this value and the remaining ones, and also for the y values. So we don't know, are there any values here in between? How do they look like, right? So that is the main reason why these outliers have an influence that is often misleading. Okay, yeah, so and they can either increase or decrease the correlation coefficient. We will see examples in a second. And so, and then again, so the smaller your sample, the larger the influence. Okay, so here, so this is actually from a paper that I would recommend so that everyone to read. It's, I think, relatively easy to understand, and has many nice illustrations and examples on the so misleading conclusions from from sample correlations and examples from real publications. I will post that on Blackboard tonight as well. So here, what is shown here is, so the first correlation coefficient, R, is always the Pearson correlation coefficient, and the second one is RS, is a Spearman correlation coefficient. It's a correlation coefficient for ordinal data, so it's based on ranks. And so this is the a corrected correlation coefficient that the authors recommend, but so you don't need to worry about that too much. So so the most important thing is, so this is Pearson correlation, and then it's also interesting to look at the Spearman correlation. So if you have only one outlier, right, so then we see so that the actually the Pearson correlation is pretty high, right? And it's also the corresponding P is low, so that would be considered like a strong correlation and a significantly different from zero. And the Spearman, so basically for Spearman, this correlation coefficient is reduced, so it's lower. It has something to do with that Spearman actually does not care so much about the actual values. So Spearman cares only about the ranks. So basically Spearman is Pearson correlation based on ranks, not on the actual data. That's why only the order of values plays a role for Spearman, but not the magnitude of the values. And that's why Spearman is less sensitive to outliers than Pearson. Okay, so here we have several outliers, and again, so in the paper, the authors have their their own algorithm to determine or to detect outliers. So there are several on the market, basically, that have been suggested. It can be difficult actually to always determine outliers by eye. So it's not. So that's why certain more objective or quantitative measures have been suggested. But it would be a little bit beyond the scope of this lecture to discuss all of them. So that's why I referred to this paper that's suggesting one, but there are others. Okay, so, and then you can see if with their, so with their corrected correlation coefficient that basically takes into account, so this undue influence due to outliers, the correlation would not be significant anymore, right? So in this case. So here we have several outliers again. So Pearson is higher than Spearman. Spearman in this case would not be significant, and then of course their corrected value as well. Okay. So and here, so here is this case where we actually so don't have outliers, but it's a split cloud data pattern, where actually, so we might have sampled from two. So either we made a mistake when drawing the sample, right? So that we sampled from the extreme ends of our distribution, or we actually have two different populations here. That's also possible. So we can't be sure, and because we don't know whether there are any values here in between and what they look like, so so these conclusions here might be extremely misleading, right? So here Pearson would estimate a super strong relationship between so the two variables, and so and even so this corrected measure, because it only takes care of outliers, would come to similar conclusions, right? So it cannot deal with so this split data cloud pattern here. So, but I would never interpret something like that, all right? So that is red flag here. So if you see these two, and in themselves, right? So within these two data clouds, there's no obvious, no clear association. Okay, so the interpreting the correlation coefficient without further knowledge or collecting more data is absolutely inappropriate. So if that happens to you, you have to run the study again. So you have to collect a new sample, make sure that you're sampling, that you draw a random sample or getting as close to it as it gets, and then see whether you can replicate that or whether it looks better the next time. Right, so here we have a case where outliers actually mask an existing correlation. So these two values here, right? So they're flagged as outliers. And so Pearson correlation actually says there is no, basically, so not significant, also if anything, then just a very weak association. Spearman is a little bit better. And so this corrected method that they're using actually says, oh yeah, so there's quite a strong relationship between these two variables. And it's also significant, right? So if you disregard these two outliers. All right, so there are more examples here. So the point is always the same, right? So the red circles are outliers here. So if you don't take care of outliers properly, so then you might come to very, very, very wrong and misleading conclusions about the true association between two variables. And it's not always easy to detect outliers by, so we may want to refer to quantitative measures. Okay, so this is just a summary here. And then I will stop for today. So this is just a summary of the assumptions that we need to check when we're running a correlation analysis, right? So first, so we have to check, is there actually a linear relationship between the two variables, and that has no implications for the statistics as such or for the confidence intervals. It just tells us how valid is our model. Right, so maybe a linear model of a linear relationship is simply not valid if there's a curvilinear relationship between the two variables. So we have to worry about the normality assumption, especially for small samples, and if we want to calculate significance tests and confidence intervals. Yeah, if all these assumptions are met and we have no outlier problems, then we can use Pearson's R. So here we have to go into further diagnosis. And so otherwise, if we have, if the data are not normally distributed or we have outliers, we want to bootstrap our confidence intervals. We want to use more robust measures, so more next time of association, right? For our call for our two variables. All right, as I said, so let's stop here for today. In the next week, we will talk a little bit more about non-parametric association measures, so the Spearman's rho and Kendall's tau. And then we will also talk about the association between categorical variables. All right, so on Monday, so in our R lab session, we will basically do the correlation analysis in R, and we'll focus a lot on outlier tests and checking the assumptions, and because doing correlation R itself is trivial. So we will basically put more emphasis on testing the assumptions, and then hopefully also I will be able to show you how to bootstrap confidence intervals and so possibly do a permutation test if the assumptions have been violated. All right. Okay, any questions? No. Okay, super. Then, yeah. Wish you a nice week, and as I said, so next Monday, so I will also post the next next month, yeah, would be good. So I will post assignment number 4 later today, and I know that you're all still working on assignment 3, but please try. So I mean, you probably not super much, don't know how much time you have over the weekend, but it would be really, really great if you could try to take a look at least before our meeting on Monday. And so I think that might be much more beneficial, right? So as I said, so we will also reserve some time to work on assignment 4 on Monday, but so the better you're prepared, the more beneficial. Okay. All right.